Hi, since we haven't started soon, I will record my lectures. All you have to do is click on the link. If you have any questions at all, please post them in the discussion board, and either I will answer your questions or hopefully your classmates. Let's begin. Section 1.4, Piecewise functions. These functions are pieces of functions you've already graphed. We are, as you can see in the first example, we are graphing linear functions, but only pieces of them. Let's take a look at part A. Can you tell what the y-intercepts of these graphs are without having to graph? Well, in the first function, part A, we have that the line y equals 2x is defined for everywhere except where x equals 0. And I'm looking at this here. For the second part, we have y equals 1, but it's only defined at x equals 0. Now, recall that the y-intercept is where x is equal to 0. Of these two functions, which function is defined for x equals 0? If you said the second one, then you are correct for y equals 1. Therefore, we're going to use y equals 1 as our y-intercept. Notice there are no x values. Therefore, I don't have to plug in x equals 1. All we say is that the y-intercept is at y equals 1. In other words, 0, 1 is our y-intercept. Okay. For the second one, and we'll come back to part A since we haven't even started answering the questions. For part B, again, the y-intercept is where x equals 0. In order to figure out which function we need to use of these three, we need to see which function is defined for x equals 0. And I'm actually going to work my way from the bottom first and then up. Okay. If you look at the third domain, this one's only defined for x is greater than 1. Therefore, it's not defined at x equals 0, and we cannot use this one. This one's only defined for x equals 1. Again, we cannot use this one. Here, x is between -2 and 1, including -2. Therefore, this one is defined for x equals 0. And we are going to use the first part of this function to find our y-intercept since it's defined at x equals 0. In this case, we do have to plug in x equals 0, and we get y equals 3. And finally, our y-intercept is 0, 3. Okay. Let's go back to part A and answer the rest of our questions. We are first being asked to find f of 0. Recall that f of 0 just means that x equals 0. Well, we already know the answer to this one because it's just our y-intercept. So f of 0 equals 1. We are also being asked to find f of 3. Okay, let's go back to our piecewise function. Where is x equal to 3 defined? Is it for y equals 2x or is it for y equals 1? If you said y equals 2x, then you are correct. And the reason it's defined for y equals 2x is because y equals 2x is defined everywhere except at x equals 0, which means that it's defined at x equals 3. So let's go ahead and use 2x, but we're going to plug in our 3 into the 2x, and we get that f of 3 is equal to 6. Box this answer too. Okay. Next, we are being asked to graph. Notice that both y equals 2x and y equals 1 are lines. Therefore, to graph these lines, we're going to use the y-intercepts and the slope. In case you're having trouble seeing where I'm at, I'm right here. Okay. What is the y-intercept of y equals 2x? Recall that the equation of a line is mx plus b, where m is the slope and b is the y-intercept. Well, mainly y-intercept is 0b, since that's how you write. Remember that. Okay. So in this case, in the case of y equals 2x, the y-intercept is 0, 0 because we have no b. And the slope is 2. Okay. So let's go ahead and graph that one before we move on to the other one. We'll use purple for this one. Okay, this is my purple one, just so you know which graph I'm graphing. Okay. I'm starting at the y-intercept, which is 0, 0. And then I'm moving up 2 and then to the right 2. So rise over run. Rising 2, so 1, 2, and then over 2. Over 1. We can do another one up 2 over 1, and so on and so forth. And this is the equation or the graph of our line. But there's one thing that we're missing here. We have to look at the domain of y equals 2x. Let's go back to our original piecewise function. Y equals 2x is only defined where x is not equal to 0. Therefore, I need to go back to my graph and actually delete that point at y equals 0. Or the point 0, 0, and draw an open circle because our graph is not defined. And it's a little bit crooked, so I'm actually going to oops, now it's really crooked. Try that again. That's better. I just want to make sure that my slope is correct, and it's not. Let's try this again. When I erased it, I lost my points. So we started at 0, 0, rise 2 over 1, rise 2 over 1, down 2 over 1. Okay, let's try one more time. Okay, this is better. Okay, so as you can see, we just graphed our line and there's an open circle there. Okay. And this is y equals 2x. Now we're ready to graph y equals 1. Let's use blue for y equals 1. Again, we have to look at the domain of y equals 1. The domain of y equals 1 is x equals 0. So when we graph y equals 1, and I'll graph the entire line first so you can see what y equals 1 looks like. So this is the graph of y equals 1. But we are only graphing y equals 1 for x equals 0. That means this entire line is gone, and we're actually only graphing this dot here at 0, 1. So this is the graph of y equals 1. It's just a point, since it's only defined at x equals 0. Finally, let's look at our domain. Remember that the domain is all the values of x for which the function is defined. Well, this function is defined everywhere. And there is an open circle at 0, 0, but we are still defining our domain at x equals 0 because there's a closed circle at y equals 1. And our range, on the other hand, goes from negative infinity to 0. At 0, we stop because there is an open circle. And then we write parentheses to show that it's not included. And then we continue again from 0 to infinity.